Welcome back to the sixth seminar of our Fik3505 course in wireless multiple access protocols. In this seminar we're going to cover collision resolution protocols. The textbook material that we're going to cover in this seminar are found in chapter 5 of the Raman City book. Looking at our protocol classification, we are still in the lower left-hand corner on contention protocols, and we're going to look at dynamic and static resolution schemes using either probabilistic time of arrival or station ID ways of resolving conflicts. The key question we're going to ask in this seminar is whether we can do better than the probabilistic conflict resolution schemes proposed in the ALOA schemes. In an ALOA scheme, stations transmit, and when a collision occurs, they draw random numbers and they delay their retransmissions according to these random experiments and hope that in the future there will be no further collisions. So the question is, can we do this more efficiently by using deterministic schemes? And so this is a situation we have here. We have stations transmitting, and here station 1 transmit the packet and station 2, and they don't experience any collisions. And then in the same slot, station 5 and station 9 happen to transmit the packet each, and we have a collision. So what we would do in a lower setting is that station 9 and station 5 would draw each a random number, determining how long they want to delay their retransmission of the packets. But what if we instead do a deterministic resolution, that we go into a conflict resolution phase where we, by some deterministic scheme, resolve the conflict? If there are very, very few stations, of course, the simplest way of doing conflict resolution is to let the system enter a TDMA mode, so that stations 1 to 9, for instance, get 1 slot each, so we can be guaranteed that we can resolve the conflicts in these 9 slots. And after we have done this conflict resolution, we go back into the free access mode. A key question is what happens if we have large sets of stations. Then the simple TDMA solution doesn't work, and particularly if we have infinite amounts of potential transmitting stations. So we need to find other solutions. A way to organize the systematic resolution of a conflict is the binary tree protocol. Here, 2 or more stations have been involved in a conflict, and that starts the collision resolution interval. Now assume that all stations that have been involved in the initial conflict here in slot number 1, they participate in the conflict resolution, whereas all other stations that haven't been involved here, they keep silent until the conflict resolution interval is ended. What we do here now in this binary tree is that the involved stations, they flip an imaginary coin with some probability they flip a 0, and with probability 1 minus p they flip a 1. And let's assume that a number of stations have flipped a 0, and there are 2 or more, so they will be transmitting in slot number 2, and since there are 2 or more stations transmitting there will be a collision. And as soon as we have a collision here, we repeat the procedure, and all those stations that have been involved in the second collision, they now again flip a coin, and some will flip 0 and some will flip 1. In this particular case, we see that in slot number 3 there was no station flipping a 0, so that slot will be empty. And then we continue with those as soon as we reached a leaf in the tree, a 0 or a single transmission, we don't have to split the tree anymore at this point. So then we can go back and go to the ones that flip the 1, and then slot number 4 we will have another collision, and we flip zeros and ones again, and then we find that in slot number 5 and 6 there will be ones, so which we have reached leaves, so we don't have to continue with this branch of the tree. So we have to go back to the original collision and look now at the ones that flipped 1, and so on, and then we keep on going until we reach the final leaf of the tree where the collision resolution interval ends. So this brings us to quiz number 1. Let's assume that we have a binary tree protocol, and we instead of doing random experiments, we use the unique ID numbers of the stations. So let's assume that we have a group of 16 stations and they're numbered 0 to 15. And these IDs are used to resolve conflicts. And so we assume that the most significant digit is used in the first step, and then if we need to branch more, the second most significant digit is used, and so on. So the questions are, how many slots are needed to resolve a conflict between stations if stations 5, 8 and 13 are involved? And what is the maximum number of slots needed to resolve a conflict under high load conditions? And the number of slots in both cases include the initial collision. As usual, you pause the recording at this time and you figure out the correct answer. And when you're done, you resume the recording. So here are the correct answers. First, we write out the station IDs in binary for 5, 8 and 13. And then we see what happens with the collision resolution. In slot number 1 we have the collision of the 3 stations, and in order to resolve the conflict now we branch the tree according to the first digit, and then we see station number 5 will have a 0 in the most significant digits, and stations 8 and 13 will have 1s. So slot number 2 will be occupied by station number 5 alone, so we have a successful transmission there, and that branch of the tree is resolved. So then we go to the stations with the 1s in the most significant digit, and we have another collision between them, between station 8 and 13 and slot number 3. So then we look at, we branch according to the second most significant digit, so we branch according to the 1, 0 and 1, 1 path. And then we see that 1, 0, that's the number for the station number 8, and 1, 1 is the beginning leading digits of station number 13. So we have successful transmissions. So the whole interval has 5 slots. So the collision resolution interval to resolve these 3 station conflict is 5. What happens when there's very high load, and what is the maximum length of the conflict resolution interval? Yeah, that happens when all 16 stations collide at once, and in a binary tree then we get one first collision in the first slot, and then we have to branch into 2 different branches, and then there will still be collisions, and then we have to branch into 4, and then we branch into 8, and then finally we get 15 leaves. So the total, then we get 16 leaves, and so the total number of slots needed are the 15 collision slots and then 16 successful slots. In total 31 slots. There's an alternate procedure to do conflict resolution, is usually referred to as a stack protocol, but that is very similar to the binary tree protocol. You know from computer science that trees often can be represented in stacks. So what happened in the stack protocol is that we push groups of stations onto the stack. So if we have a collision, then we split the number of stations into two groups, those who flip 0 and those who flip 1, and then we push those that have flipped 1 onto the stack, and then we start resolving the conflict among those that have flipped the 0, and then we do again in that group, and if we have another collision, we have to split that group into two subgroups, and then the one that we handle directly is on the top of the stack, the other one we push on the stack into level 1, and so on. And whenever we have a successful transmission, we pop the stack. So let's do a performance analysis of the binary tree protocol. The critical parameter here is the length of the collision resolution interval. The longer the conflict resolution interval, the worse is the performance. So we assume that if we have n colliding packets, we denote by b tilde n the random number that is the length of the conflict resolution interval. And we will be interested in finding out this ratio, which is the number of successful transmissions in the length of of the collision resolution interval, or the expected number of packets that we can transmit in the expected length of the conflict resolution interval, and that will be the effective service rate. And we will see that that will be close to the as n goes to infinity, that will be the maximum throughput of the protocol. We also realize that the binary tree protocol works in a way that for each collision we split the tree into subtrees, and the subtrees will have the same statistical properties as the original tree. So when we have a collision, it will take one slot, and then we split the tree into one subtree where there will be I packets, given that I flipped the 0, and the other n minus I packets will be in the other branch. So the total number of slots in a conflict resolution interval, given that I flip 0, is given by this expression. And the probability distribution of I, given that there are n packets in the collision, is a simply binomial probability distribution, provided p is the number of stations that flip a 0. And plugging this into the above expression, we get the expected number of conflict resolution slots, given that there are n packets involved in the initial collision. And we have the boundary conditions that if there are 0 packets or 1 packets, there will be only 1 slot in the CRI. And so we can do some computation and find the expected number of slots in a CRI in this recursive equation. And this recursive equation has to be solved numerically, and this is how we do it. And you can see here that as we increase the number of packets in the initial collision here from 1, 2, 3 to 5 in the first row, and 11 to 15 in the lower row, we can see that the ratio n divided by bn converges to a number that is slightly higher than 0.35. In Roman City, then we can show that we can bound the moments, the first moment of the conflict resolution interval Bn in the two expressions on the left-hand side. It can be shown to be lower than alpha m times n minus 1, or we can show that the ratio has to be larger than 1 over alpha m, and alpha m is the critical throughput of the system. And we can show that for this system, the system will be stable for lambda stars that are in the range of 0.346 to 347. So let's apply this technique to the simple example we have with a finite number of users, with the 16 users in quiz number 1. What would the maximum throughput be in such a system? As usually, pause the recording at this point and find out the correct answer. And when you're done, restart the recording. So here's the correct answer. At very high loads, we will have all stations have a packet to transmit, so there will be 16 stations colliding in every conflict resolution interval, and we found from quiz 1b that the length of that conflict resolution interval was 31 slots. So then we can compute the ratio n divided by b will be 16 over 31, and so the maximum throughput has to be less or equal than 0.51. Yeah. Roman City also shows some simple modifications of the binary tree protocol, and one obvious modification is the following. In our example, we can see when slot number 3 was empty and slot number 2 held a collision, then we already know that there will be a collision in slot number 3. So we can simply skip that transmission and branch immediately in slot number 3. By that we save one transmission slot, so the conflict resolution interval can be limited to 10 in this particular example. And this gives a slight improvement of the maximum throughput to 0.38. And we can also show that in this particular case we shouldn't have equal probabilities to flip a coin to 0 and 1. Instead we should have slightly skewed flipping here, that the p should be 0.42 roughly in order to get the maximum throughput. In the binary tree protocol, we have assumed that we use coin flips or ID numbers to do the conflict resolution. An alternative that has been proposed is the epoch mechanism, where we use the arrival times of messages to resolve the conflict. And this is how it works. We assume that the time axis for arrivals is split into intervals of size delta. It's called the epoch interval. And then we treat all those packets arriving in, for instance, in 0 to delta. We treat them in the conflict resolution interval, and then we can use the arrival time to split the interval into smaller and smaller pieces until we have resolved the conflict time. The epoch interval delta has to be chosen in an effective way in order to maximize the performance of the conflict resolution. This can be shown to give very good performance results when it comes to maximum throughput. Of course, the drawback is that we decouple the arrival times from the actual conflict resolution. So we lose some control over the delay in the system. But this is done in order to maximize the maximum throughput. So this is how it works. We have a first transmission, and in this interval, all the packets arriving in time between time instances A to G will be transmitting in the first slot. And in this particular example, we have a collision. So what we do now is that we split the interval in half, and we now let all the stations with packets arriving in interval A to D transmit the first half of the interval, and those are allowed to transmit in slot number 2. And we have another collision, so we now have to split that interval again, and we have the interval again, and now we transmit over interval A to B. And in this case, there is no successful transmission at all. And then we go back in our tree, and then we go to the other half of the interval, B to D, and that will be in slot number 4, and so on, until the conflict is resolved, in this case in 11 slots. And then we start with the next interval, which will be G to K, which is the next epoch interval of size delta. And this graph shows how we should optimize the parameters. First, we want to find out how to choose the delta, and so we can see here, using the auxiliary parameter lambda times delta equal to z, the performance is maximized around z just above 1. And we can also see how the splitting of intervals should be chosen. In this particular example, we can see p equal to 0.5, corresponding to that we split the interval in halves. That gives the best performance. And compared to the binary tree protocol, we see a slight improvement again. So lambda star for this protocol has to be less than 0.43. So we can improve even a little bit more on the epoch tree protocol, and that protocol is called the clipped tree protocol, and this is how it works. We again start with an epoch interval delta, and we start our tree to resolve this interval. And we have a collision in the first slot, A to G again, and then again we have the interval and have another collision in the second interval, and then we keep on going until we have resolved the whole first interval. So we now transmitted all packets arriving in the interval A to D. What we now realize is that if we have no information about what has happened in the right interval, and we can see that the intervals in the packets in the interval D to G, they are Poisson distributed, and they are independent of what has happened up to time instant D. So this means that instead of resolving the right-hand interval, the optimum thing is to actually from this point use a new epoch of size delta, and to keep resolving that, and this we do in this tree, and so on. And this procedure will find us that once we have resolved up to time instant f, there is again no information of what goes on to the right of f, and we do a new epoch interval of size delta, and so on. And this procedure can improve the throughput even slightly more, and the throughput here is 0.487. So that brings us to the summary for conflict resolution schemes, and we found that systematic resolution schemes actually perform better than random retransmission. And we've looked at the binary tree schemes using coin flips or ID. And we also saw the very high performing epoch mechanism schemes that uses the arrival time, and they decouple the arrival time from the transmission interval. And these schemes have the highest known throughput. On the other hand, the delay properties are not so good.